So in the last video, we stopped at finding the coefficients d1, d2, d3, d4, which we got from the boundary conditions that need to be fulfilled at the potential energy barrier. And during the last video, we also said that for the calculation of the transmission coefficient, T, in which we are actually interested in, we just need the coefficient D4. So, or D2, sorry, this guy here, D2. And as already set up in the last video, we just can solve this matrix vector equation and obtain this vector here containing the D constants. So one way would be to invert this matrix, but since we are only interested in D2, we can also work with Cramer's rule from linear algebra. So apply Cramer's rule, then D2 would be or else first write the determinants. So this is still the same matrix as we had on the last slide. And here in Cramer's rule, the matrix stays, or the entries of the determinant here stay the same. Just because we're interested in D2, the second column of the determinant will be exchanged by the entries of the vector at the right-hand side here. So let's copy everything here, 0, 0. Then here we have now 0, 0. E to the power I times A times D. And here we just copy the entries. And this is D2. Now we can define this with a different, or let's specify some symbols for the different determinants. So this would be D21 and D22. So D22 is actually easy to calculate because the entries here are 0. Therefore, from linear algebra, it follows that D22 equals the determinant of minus IA, 11. It's actually this sub-determinant here and this sub-determinant here yield the value of D22. This, if you calculate it, is 4 times I times A times B. So the strategy to solve for D21 so I write again here this determinant. But the strategy would be to rearrange columns and rows of this determinant such that we yield in a determinant where these lower 4 entries here are 0 as well. To be able to apply a more simple formula to solve for the value of the determinant. So the third thing is we take the second row and subtract the second row I A times from the first. So this, according to the rules of determinant operations, does not change the value of the determinant. So the rest stays the same. Just copy. E to the power of P times T D So the next thing is that I multiply the third row. Let's use a different color here. Then I multiply the third row with minus I times 1 over A. And this modifies the value of the determinant, meaning that we have to multiply it with the inverse of this, which is minus, which is AI. And now I subtract the third row from the fourth row, which yields can just copy. Now the fourth row changes. So now the next step before we are able to calculate the value of the determinant in a more easy manner to switch row 1 and row 3. So this changes the sign of the determinant, and eventually we get a matrix. It looks like this. Or determinant looks like this, sorry. And here, these values here, I don't calculate anymore because we do not need it. But now we are at the point we can calculate the value of the determinant more easily. It's just the determinant of this sub block here times this block here. And eventually I also already write down the expression for D2. Previously we have already calculated the value for the denominator here, and above the line this determinant is evaluated to be the following value. I do not carry out every sub-step. Just give the final expression from here. So, with the following addition theorems, or the following theorems, the cos h of x in general equals e to the power of x plus e to the power of minus x divided by 2, and the sine h of x equals e to the power of x minus e to the power of minus x divided by 2. We can rewrite this expression And now we can already give a value for the transmission coefficient. Also with the help of still the following addition theorem. Namely, it is that cos h squared of x times minus the sine h squared of x equals 1. With this theorem and with expressing b and a in terms of v naught and e, we finally arrive at the following expression for t, our transmission coefficient, which is one plus 1/4 v naught squared over E. E again is the energy of the incoming particle that hits the potential energy barrier. T again is the width of the potential energy barrier. Finally, mathematically, we are done. Now it's we have to interpret this. Therefore, let's rewrite it a bit. And let's define that E equals x times v naught. So we are expressing E as a fraction of v naught. Or x is the ratio of E divided by v naught. So this gives us now the following expression. So now I define here also small v naught. So before I end it, v naught equals square root of 2md v naught over h bar squared, and here the square root of 1 minus x. Now I have already plotted this function t of x for different values of v naught. But the first thing is that you see that since t is a measure of transmission likelihood, that for a wave that has for an incident wave that has lower energy than the potential energy barrier, the probability that it will pass through the barrier is higher than 0. That's the first observation, I would say. And here we have different values for V naught, and V naught is proportional to V naught times the potential energy barrier, or the width of the potential energy barrier and the value of the potential energy value at the barrier. And that you see that if V naught goes up, the probability of transmission goes down. Same is true for the width of the potential energy barrier. So again, to sum up, the message here is that the probability that the particle will go through the potential energy barrier, despite that its energy is lower than the potential energy barrier value, is not zero, and the transmission coefficient increases with decreased width of the potential energy barrier, and increases with decreasing thickness of the potential energy barrier, and it also, the transmission probability also increases when the value of V naught is lower, as illustrated in this graph. And here, just for completeness, so actually here in this last equation, we have a look here until the value of 1. So here at the value of 1, the value of E equals the potential energy value at the barrier. And we have now interpreted this region here before. But when x equals 1, this means that t of x is not defined first. And then if x is greater than 1, then this sine h term is complex, or the value of the root here is complex. Therefore, for this purpose, I have used the identity that I times sine of x equals sine h of I times x for plotting. And finally, now we have made more, I would say, a graphical interpretation of the analytical result we have obtained. Finally, I think to more rigorously see the dependence of the transmission coefficient upon the barrier height and the barrier width, it is interesting to calculate the following value. Namely, let's write down again this equation. So, sorry. T of x first, and then I will state which value I would like to calculate. V naught, same definition as before. And first then rewrite this expression with a function, with the function f, and f should be sine h V naught square root of 1 minus x divided by square root of 1 minus x. Now with this definition, tx becomes 1 or 1 plus 1/4 f of x squared times 1 over x. And we would like to calculate the limit of t von x when x approaches 1. And therefore, so this is what we are interested in, and therefore first calculate the limit of f of x when x approaches 1. Let's do this on the next slide. Write again this expression here for fx. So with the rule of L'Hopital, just mention it here, rule L'Hopital, since we cannot directly calculate the limit of this expression because both terms here are 0 for x equals 1, we have to take the first derivative both expressions, and when this is the case, according to the rule of L'Hopital, the limit, they are equal. So first here, takes the derivative with respect to x, again here. So this is the derivative of the term within the brackets. And the derivative of the sine h is the cosine cos h. Here, same value for the denominator. Finally, this limit here has the value of v0. And from this it follows, because here we calculated the limit of f of x when it approaches 1, and therefore, since this also goes to 1 as x goes to 1, we can just plug in the value of v0 squared here, and we arrive at the following expression. That the limit as x goes to 1 of t of x equals 1 over 1 plus v0 squared over 4. And this gives now a more analytical explanation of how the transmission probability depends on the properties of the potential barrier, since v0 is proportional to v0 times d, the width of the potential barrier. So as v0 goes up, t goes down, and as d goes up, t goes down as well. This more analytical expression. I hope you find this useful, and actually that's the final result of this video lecture. Hope you like the content, and see you again if you wish.